how are we going to create our own quantized layer? Well, this could be MATLAB, or this could be some other framework that you are trying to do this. Well, yes, in future MATLAB will have this quantization capability, or even if you're using Python, most frameworks already have it. So why are we doing this? Because when you're doing embedded engineering or embedded research, embedded deep learning research or embedded deep learning engineering, you will need your own alterations. You will need to design a specific network. So doing such a practice will help you understand many details of the system so that you could make your own alterations, you could contribute new things, and actually if you're doing a research about it, if this is a part of your master's or PhD studies, I strongly recommend doing this. I mean, if you're doing a master's on embedded deep learning or a PhD on embedded deep learning, I strongly recommend writing your own quantized layers to any platform, framework you're using, whether it's TensorFlow or MATLAB, doesn't matter. Because it will give you a clear idea of how this guy trains itself, how the training takes place, so that you could just debug your training, debug your quantized layers, and you'll get the idea. And once again, before I get to the steps, because I got only this slide for this video, please read this paper. This is a fantastic paper, guys, because they cover nearly all of the fundamental stuff. These guys are from Google, and TensorFlow belongs to Google. Actually, these guys tell us how they did this for TensorFlow in this study and in this white paper. So it's public, it's from Arsiv, and they give the details of how they do it. Please read this. How to update the weights, what is the necessary condition. So when you're previous week we have discussed these accumulations and overflow. You remember they discussed the overflow in the accumulators, how to overcome this, where to keep 8-bit information, where to keep 32-bit information, how to keep biases about most of the time while you're quantizing your values, you need the exact value 0, how to keep zeros, how to handle the ReLU layer. Very important questions are being answered in this fantastic paper. I strongly recommend you guys to read the entire paper. And if you have got any questions, please just ask them to me. I'll prepare a question and answer video session as well. So, okay, what is the basic idea? The basic idea is twofold. You've got layers, and which you have to change. You have to create the quantized versions, and there are some additional layers that you have to create. So there are in their idea only two tensors matrices to be quantized, which is the weights, as you can see if you look at the difference, the quantization of the weights, and the biases, of course. Weights, by weights they refer to both weights and the biases, and they quantize the actuations. So how to quantize the weights inside a layer? Well, you will need to create the quantized version of the convolutional or other multiplication layers. Whether it's a convolutional layer or a fully connected layer, you rewrite the quantization of fully connected layer. So in your MATLAB, if you're doing it for MATLAB, you are going to create a custom layer, which is a quant convolutional 2D kind of. You're going to create that layer. Just like I created this distribution layer. It's going to be quant something, which is a child of an NN-led layer, convolution layer, kind of. You're going to rewrite it. And that layer, when you rewrite it, will have the ability to quantize its weights in the forward run. It won't change anything in the backward run, only change the forward run. Plus, you will need to do one thing as well. You will need to create a new layer, which you can call the quantization layer. That quantization layer will quantize an input and it will provide quantized outputs. So in this part, you have ReLU and you have output, which are actuations of this ReLU layer. You feed this to the quantization layer, it gives you quantized output. So the forward path is quantized, and again, backward path is unity function. The backward pass doesn't change anything. So in your training graph, this layer, this new layer, this quantization layer, in its forward pass will quantize values. But in its backward pass, what it does is it simply provides the same gradient to its preceding layer. So you don't cheat. So any gradient, it's passed without a change. If you can just add these two capabilities to your framework, you can create any quantization-aware training framework you want. And when you run the backpropagation, you'll be able to do backpropagation with a quantization-aware manner. So that's the idea. I strongly recommend you to read this paper. And if you are doing a embedded deep learning study research, to do this practice in any framework you want. That's a very nice practice. And I think that concludes our discussions about quantization-aware training. This is a very nice title, and it's a very, very new title. People are working on it in there are many papers, and if you can do anything new, it will definitely be a new study. And starting with the following weeks, we are going to put things on top of this quantization-aware training stuff and see different architectures like mobile nets, like binary nets, or like ternary nets, and how they use these ideas to create their own aggressively quantized deep learning nets. Thank you.